Hello there, and welcome to Sleep Science, where we explore fascinating science in a quiet, relaxing way that helps your mind unwind and drift off to sleep. Before we begin tonight's journey, feel free to share what time it is and where you're listening from. It's always wonderful to know where these gentle explorations are floating off to. Tonight, we're going to meet a star that's older than the universe. How fascinating. This isn't just a story about one confused star, though. It's about how science works when faced with the impossible, how we measure the unmeasurable, and what happens when the universe seems to contradict itself. We'll wander through stellar archaeology, cosmic calendars, and the patient detective work of astronomers who refuse to give up on a good mystery. So settle in, perhaps with something warm to sip, and let's drift into the story of a star that shouldn't exist and how that impossibility led us to understand time itself a little better. There's a star out there that's been making astronomers nervous for decades, not because it's particularly large or bright or threatening to explode. No, this star's crime is far more peculiar. It appears to be older than the universe itself, which is a bit like discovering your great-aunt Muriel was born before the invention of time. The star in question goes by the rather unpoetic name HD 140,283, though astronomers have given it the much more charming nickname Methuselah, after the biblical figure who supposedly lived 969 years. In stellar terms, that's practically infancy, but the name stuck because this particular star seems determined to outlive everything, including logic. Methuselah sits about 190 light-years away from us in the constellation Libra, which means the light hitting your eyes tonight actually left that star around the time your great-great-great-grandmother might have been learning to walk. It's not visible to the naked eye, so you can't wave at it from your backyard, but it's been quietly shining there, minding its own business, probably unaware that it's been causing existential crises in observatories around the world. The first hint that something was unusual about this star came in the 1950s, when astronomers began studying its chemical composition. Stars, you see, are like cosmic cookbooks. They tell us what ingredients were available when they formed, and Methuselah's recipe was interesting. It contained almost no heavy elements, what astronomers call metals, though they mean anything heavier than hydrogen and helium, which would make a periodic table enthusiast twitch slightly. This lack of heavy elements was the first clue that Methuselah was ancient, very ancient. The early universe, you see, was a simpler place, chemically speaking. After the Big Bang, there was mostly hydrogen and helium floating around, with just a dash of lithium for flavor. All the heavier elements, carbon, oxygen, iron, the stuff that makes planets and people possible, had to be cooked up inside stars and then scattered around when those stars died in spectacular explosions. So, a star with very few heavy elements is like finding a recipe that calls only for flour and water. It suggests the star formed when the cosmic pantry was still pretty bare, before generations of stars had lived and died to stock the universe with more interesting ingredients. But here's where things get delightfully complicated. When astronomers tried to figure out exactly how old this chemically primitive star was, they ran into a rather embarrassing problem. Their calculations kept suggesting that Methuselah was around 14.3 billion years old. That might not sound particularly shocking until you realize that the universe itself is only about 13.8 billion years old. It's a bit like carbon dating a wooden chair and discovering it was built before trees existed. The star seemed to be a cosmic impossibility, a stellar senior citizen that predated its own birthday party. And before you ask, no, this wasn't just a simple math error that could be fixed with a better calculator and a strong cup of coffee. Multiple independent studies kept arriving at the same uncomfortable conclusion. This star was too old to exist. Now, you might wonder how astronomers measure the age of something that's been burning for billions of years without any sort of cosmic birth certificate. It's actually rather like detective work, but with more mathematics and fewer magnifying glasses. Stars age in predictable ways, burning through their fuel at rates that depend on their mass and composition. By studying a star's temperature, brightness, and chemical makeup, astronomers can work backward to figure out when it must have formed. It's similar to looking at a candle and, by measuring how much wax remains and how fast it's burning, figuring out when someone lit it. Except the candle is millions of times larger than Earth and the flame is nuclear fusion, but the principle holds. HD 140,283 also had another story to tell. Its motion through space suggested it was what astronomers call a halo star, one of a population of ancient stars that orbit the Milky Way in vast, looping paths rather than settling down in the galactic disk like our Sun. These halo stars are the cosmic equivalent of nomads, wandering through space in eccentric orbits that take them far above and below the galaxy's main plane. This wandering lifestyle fit perfectly with the star's ancient chemical signature. Halo stars are thought to be some of the oldest objects in our galaxy, formed in the early days when the Milky Way was still figuring out how to be a proper galaxy. They're like the universe's senior citizens, holders of ancient wisdom and stories from a time when galaxies were young and the cosmos was still sorting itself out. But being old is one thing. Being older than the universe itself is quite another. The discovery of Methuselah's impossible age created what scientists politely call a discrepancy, and what everyone else might call a cosmic headache. Either our understanding of stellar evolution was wrong, our measurements of the universe's age were off, or this particular star had somehow managed to break the fundamental rules of space and time, which would be impressive but rather inconvenient for physics. For years, Methuselah sat there in the sky, 190 light-years away, quietly burning hydrogen and inadvertently challenging everything we thought we knew about cosmic chronology. It became a gentle reminder that the universe still holds surprises, even for those of us who think we've got it mostly figured out. And so began one of astronomy's most endearing mysteries, the case of the star that refused to respect the cosmic speed limit of age. Stars don't carry birth certificates, but they do leave clues scattered throughout their light. Like cosmic archaeologists, astronomers have learned to read these stellar stories, piecing together the biography of a star from the whispers hidden in its glow. It's detective work on the grandest scale, where the evidence is starlight and the crime scene is the entire universe. Every star is essentially a giant nuclear furnace, and like any good furnace, it burns through its fuel at a predictable rate. The star's mass determines how hot it burns, how bright it shines, and most importantly for our purposes, how long it lasts. It's a bit like the difference between a birthday candle and a campfire log. One burns quickly and brightly, the other settles in for the long haul. The most massive stars are the show-offs of the cosmic neighborhood. They burn fierce and fast, blazing through their hydrogen fuel in just millions of years before dying in spectacular supernova explosions. These stellar sprint runners are brilliant but brief, like fireworks that light up the sky and then fade into memory. On the other end of the spectrum are the red dwarf stars, the cosmic equivalent of energy-efficient light bulbs. These modest little stars burn so slowly and steadily that they can keep going for trillions of years. In fact, the universe hasn't been around long enough for any red dwarf star to actually die of old age yet. They're the ultimate marathon runners, still at the starting line while the sprinters have already finished the race and gone home. Our Sun sits comfortably in the middle, a medium-sized star with a medium-sized fuel tank and a reasonably respectable lifespan of about 10 billion years. We're currently about halfway through that stellar lifetime, which means our sun is basically middle-aged, probably starting to worry about its stellar waistline and wondering where all that hydrogen went. But how do astronomers actually figure out where a star is in its life cycle? The secret lies in something called the main sequence, which sounds like a dance, but is actually the longest and most stable phase of a star's life. During this phase, stars burn hydrogen in their cores, converting it to helium through nuclear fusion. It's like a cosmic cooking show where the main ingredient is always hydrogen and the final dish is always light and heat. As stars age, they gradually change. They get slightly larger, slightly cooler, and their light shifts in color. These changes happen slowly, so slowly that even if you watched a star for your entire lifetime, you wouldn't notice any difference. But astronomers have a trick. They study thousands of stars at different stages of their lives, like looking at a photo album of people from babies to great-grandparents to understand how humans age. This stellar photo album is called the Hertzsprung-Russell diagram, and it's one of astronomy's most useful tools. Plot a star's brightness against its temperature, and you can read its age like a cosmic chronometer. Most stars fall along a diagonal line called the main sequence, and where they sit on that line tells you how old they are and how much time they have left. But HD 140,283 presented a puzzle even here. When astronomers looked at its position on this stellar age chart, everything pointed to one conclusion. This star was incredibly, impossibly old. Its temperature, its brightness, its chemical composition, every measurement suggested it had been burning for far longer than should be possible. The chemical composition was particularly telling. When astronomers spread a star's light through a spectrometer, they can read it like a cosmic ingredient list. Each element absorbs light at specific wavelengths, creating dark lines in the spectrum like a barcode. These stellar barcodes reveal exactly what the star is made of, and HD 140,283's barcode was almost comically simple. Most stars, including our Sun, show evidence of multiple generations of stellar cooking. They contain carbon forged in the cores of ancient stars, oxygen breathed out by dying giants, iron scattered by supernovas. They're like cosmic bouillabaisse, rich with the accumulated flavors of stellar history. But Methuselah's spectrum was more like cosmic bread and water. It contained almost pure hydrogen and helium with just the tiniest traces of heavier elements. This chemical simplicity was a dead giveaway that the star formed very early in the universe's history, when the cosmic pantry was still quite bare. There's something rather poetic about this stellar archaeology. Every time we look at an ancient star like HD 140,283, we're essentially looking back in time, seeing the universe as it was billions of years ago. The light reaching our telescopes today began its journey when the cosmos was young, when galaxies were still forming, and the first stars were just beginning to seed space with heavy elements. These ancient stars are time capsules, preserving the conditions of the early universe in their very atoms. They tell us what the cosmos was like before planets could form, before life could emerge, before there was anything in space except hydrogen, helium, and the patient work of nuclear fusion. The fact that we can read these stellar stories at all is rather remarkable. We're essentially cosmic genealogists, tracing the family tree of matter itself. Every atom in your body except hydrogen was forged in the core of a star, or in the explosive death of a supernova. You are, quite literally, made of stardust that has been recycling through the universe for billions of years. But sometimes, as in the case of HD 140,283, the stellar story doesn't quite make sense. Sometimes the evidence points to conclusions that seem impossible, ages that predate the universe itself. When that happens, astronomers don't give up. They sharpen their pencils, improve their telescopes, and dig deeper into the mystery. Because if there's one thing the universe has taught us, it's that impossible often just means not yet understood. And so the hunt for Methuselah's true age began, a detective story written in starlight and measured in billions of years. If you want to know how old the universe is, you need to travel back to its baby photos. Unfortunately, the universe is surprisingly good at keeping photo albums, though they're scattered across the entire sky and written in the language of light and radiation. The story of measuring cosmic age begins with a rather startling discovery made in the 1920s by an astronomer named Edwin Hubble. Not the telescope that came later, but the man himself, working with what was then the largest telescope in the world at Mount Wilson Observatory. Hubble was studying distant galaxies, trying to measure how far away they were, when he noticed something peculiar. The farther away a galaxy was, the faster it appeared to be moving away from us. This was a bit like standing in a crowd and noticing that everyone was walking away from you, with the people farthest away moving the fastest. Your first thought might be to check if you'd forgotten deodorant that morning, but Hubble realized he was seeing something far more profound. The universe itself was expanding. If you imagine the universe as a balloon being inflated, every point on the surface moves away from every other point as the balloon grows. Galaxies aren't actually racing through space away from us. Space itself is stretching, carrying the galaxies along for the ride. It's a mind-bending concept that even today can make your brain feel slightly wobbly if you think about it too hard. But here's the clever bit. If the universe is expanding now, you can run the movie backward to see what it was like in the past. If everything is moving apart today, then yesterday everything was a little closer together. The day before that, even closer. Keep rewinding, and eventually you reach a point where everything in the universe was squashed into a single, incredibly hot, incredibly dense point. That moment of ultimate cosmic compression is what we call the Big Bang, though it wasn't really a bang, and it didn't happen in a particular place. It was more like the universe suddenly deciding to exist and then immediately getting very enthusiastic about expanding. The Big Bang wasn't an explosion in space. It was space itself beginning to expand, carrying time and matter along with it. By measuring how fast the universe is expanding today, something called the Hubble constant, astronomers can calculate how long ago this cosmic expansion began. It's like measuring how fast a car is driving and figuring out when it must have left the starting line. The math gives us an age of approximately 13.8 billion years, with a margin of error that makes astronomers feel reasonably confident they've got it roughly right. But the expanding universe isn't the only baby photo the cosmos has left us. There's an even more direct piece of evidence, the cosmic microwave background, or CMB. This is the afterglow of the Big Bang itself, a faint whisper of radiation that fills every corner of space. It's like the universe's birth cry, stretched and cooled by billions of years of cosmic expansion until it's barely detectable. The CMB was discovered quite by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who were trying to eliminate annoying static from their antenna. They cleaned bird droppings off their equipment, checked every component twice, and even built a completely new receiver, but the static remained. Eventually, they realized they weren't detecting static at all. They were hearing the echo of creation itself. This cosmic background radiation is incredibly uniform, filling space with a temperature of about 2.7 degrees above absolute zero. But within that uniformity are tiny, incredibly subtle variations, ripples in the cosmic fabric that represent the seeds of all future galaxies and stars. By studying these ripples in exquisite detail, astronomers can read the universe's vital statistics, like checking a cosmic medical chart. Missions like the Cosmic Background Explorer, The Wilkinson microwave anisotropy probe and the Planck satellite have mapped these temperature variations with extraordinary precision. The data tells us not just how old the universe is, but what it's made of, how fast it's expanding, and even what its ultimate fate might be. The precision is quite remarkable. We can now say the universe is 13.799 billion years old, plus or minus about 21 million years. In cosmic terms, that's like knowing someone's age to within about 3 minutes over an entire human lifetime. Not bad for measuring something that began before there were any clocks to check. There are other cosmic chronometers as well. Globular clusters, dense balls of ancient stars that orbit our galaxy like stellar cities, provide another way to measure cosmic age. The oldest white dwarf stars, the cooling remnants of long-dead suns, offer yet another timeline. Type Ia supernovas, exploding stars that always reach the same peak brightness, give us a way to measure cosmic distances and, indirectly, cosmic age. All these different methods generally agree with each other, which is reassuring. When multiple independent techniques point to the same answer, scientists start to feel fairly confident they're on the right track. It's like asking several friends what time it is and having them all check different clocks. If they all give you roughly the same answer, you can be reasonably sure you're not running late. But occasionally, as with HD 140,283, individual objects seem to challenge these careful measurements. When that happens, it's usually a sign that something interesting is going on. Either our understanding needs refining, our measurements need improving, or we've stumbled across something that will teach us something new about how the universe works. The universe has a way of keeping astronomers humble. Just when we think we have it all figured out, it presents us with a puzzle like a star that appears older than time itself. These cosmic contradictions aren't problems to be swept under the rug. They're opportunities to learn something new, to refine our understanding, to discover that the universe is even more interesting than we thought. And so, armed with our measurement of 13.8 billion years for the universe's age, astronomers face the puzzle of HD 140,283 with both confidence and curiosity. They knew their cosmic chronometer was reliable, but they also knew the universe still had secrets to reveal. Picture finding a tree in your backyard that your instruments say is older than the soil it's growing in. You'd probably check your instruments twice, then maybe call a friend to double-check your math. That's essentially the situation astronomers found themselves in when they tried to reconcile Methuselah's age with the age of the universe itself. The numbers were stubborn and uncomfortable. Every calculation, every measurement, every different approach to dating the star kept arriving at the same impossible conclusion. Methuselah appeared to be about 14.27 billion years old, give or take a few 100 million years. Meanwhile, the universe, the thing that supposedly created the conditions for stars to form in the first place, clocked in at a mere 13.8 billion years old. It was like discovering that your grandmother was born before her own mother, which would make family reunions awkward and challenge some fairly fundamental assumptions about how time works. In the scientific community, this kind of discrepancy has a technical name: a problem. Not the sort of small problem you solve by checking your arithmetic, but the sort of large, universe-questioning problem that makes astronomers lie awake at night, wondering if they've fundamentally misunderstood something important about reality. The first reaction, naturally, was to check everything twice, and then 3 times. Astronomers are a cautious bunch, and when faced with results that seem to break the universe, their instinct is to assume they've made an error rather than that the universe has made an error. This is generally a sound approach, since the universe has been in business for quite a bit longer than human civilization and probably has a better grasp of the rules. Teams of researchers went back to their data with fine-tooth combs, which is the astronomical equivalent of double-checking your work. They re-examined the star's distance, recalculated its brightness, reanalyzed its chemical composition. They checked their instruments, verified their software, and probably consumed alarming quantities of coffee in the process. But the numbers remained stubbornly wrong. HD 140,283 continued to insist, through the quiet testimony of its starlight, that it was older than the universe that had supposedly given birth to it. The star was either lying, which seemed unlikely since stars are generally honest about these things, or something more interesting was going on. This created what philosophers of science call cognitive dissonance, and what everyone else calls a headache. On one hand, astronomers had multiple independent lines of evidence confirming the universe's age. The cosmic microwave background, the expansion rate, the abundance of light elements, everything painted a consistent picture of a 13.8 billion-year-old cosmos. On the other hand, there was HD 140,283 sitting peacefully in the constellation Libra, its ancient light carrying the chemical fingerprints of extreme age. It wasn't some distant, fuzzy object at the edge of detection. It was a relatively nearby star that astronomers could study in detail, and every detail suggested it had been around for longer than physics said was possible. The scientific method has a way of dealing with these situations, though it's not always comfortable. When observations contradict established theory, something has to give. Either the observations are wrong, the theory is wrong, or, and this is often the most interesting possibility, both are partially right, but incomplete. History is full of similar moments. When Mercury's orbit didn't quite match Newton's predictions, astronomers first assumed they had missed something, perhaps an undiscovered planet tugging on Mercury. But eventually, Einstein showed that Newton's theory was incomplete, and the discrepancy led to general relativity. Sometimes, the universe's apparent mistakes are actually invitations to understand it better. In the case of HD 140,283, the contradiction was particularly unsettling because it involved fundamental questions about the nature of time itself. If stars could somehow exist before the universe that created them, what did that say about our understanding of cosmic chronology? Were there multiple universes? Had something gone wrong with the Big Bang timeline? Or was there simply a more mundane explanation hiding in the measurement uncertainties? The situation was made more intriguing by the fact that Methuselah wasn't entirely alone. A few other ancient stars showed similarly troubling ages, though none quite as dramatically as Methuselah. It was as if the universe's oldest stellar citizens were staging a quiet rebellion against the cosmic timeline, politely but firmly insisting they were older than their birth certificates suggested. Scientific conferences began featuring sessions with titles like The Age Problem and Temporal Inconsistencies in Stellar Evolution, which sounds rather more dramatic than the actual discussions, which mostly involved people in comfortable sweaters pointing at graphs and saying things like, that's odd. But beneath the measured academic language was a genuine puzzle that touched on some of the deepest questions in cosmology. How well do we really understand stellar evolution? Could there be unknown factors affecting how we date ancient stars? Are our measurements of the universe's age as solid as we think they are? The answer, as it often is in science, turned out to be, it's complicated. The resolution wouldn't come from dramatic new theories or revolutionary insights, but from the patient, careful work of improving measurements and understanding uncertainties. Sometimes the most profound discoveries come not from overturning everything we think we know, but from getting our numbers right. The universe, it seemed, wasn't actually broken, but our precision needed some work. And so began a more careful investigation, one that would ultimately teach astronomers as much about the importance of uncertainty as about the age of stars. Because sometimes the most important scientific discoveries come from the moments when our confident measurements meet the universe's stubborn refusal to fit neatly into our categories. When faced with a star that breaks the rules, astronomers don't give up. They get more precise telescopes. And in the case of Methuselah, that meant calling in the big guns, the Hubble Space Telescope, floating serenely above Earth's atmosphere, far from the twinkling and blurring effects that make ground-based astronomy occasionally feel like trying to read a book through a fishbowl. The problem with measuring something as ancient as Methuselah from Earth is that our atmosphere has opinions about starlight. It bends it, bounces it around, and generally makes precise measurements about as reliable as trying to thread a needle during a minor earthquake. Stars twinkle beautifully, which is lovely for poets, but mildly infuriating for astronomers trying to get exact numbers. Hubble, however, sees stars as steady points of light, unblinking and crisp. This makes it perfect for the delicate work of stellar archaeology, where tiny differences in brightness and color can reveal secrets about a star's age and composition. It's like having the universe's most powerful magnifying glass, combined with the steadiest hand imaginable. The first order of business was getting a better handle on Methuselah's distance from Earth. This might seem like a straightforward measurement. After all, the star is sitting right there in the sky, but measuring distances in space is surprisingly tricky. There are no cosmic measuring tapes, and asking the star to hold still while you pace off the distance isn't really an option. Instead, astronomers use a technique called parallax, which takes advantage of Earth's orbit around the Sun. As our planet moves from one side of its orbit to the other, nearby stars appear to shift slightly against the background of more distant stars, like how objects appear to move when you close one eye and then the other. The amount of shift tells you how far away the star is, but parallax measurements require extraordinary precision. For a star like Methuselah, the apparent shift is about the same as the width of a dime seen from 2 miles away. It's the sort of measurement that makes astronomers grateful for very patient computers and very stable telescopes. With Hubble's help, astronomers were able to pin down Methuselah's distance much more precisely than ever before. They found it was about 190.1 light-years away, plus or minus 2.7 light-years. That might not seem like a dramatic improvement, but in the world of stellar dating, small improvements in distance measurements can make big differences in age calculations. Knowing the distance more precisely allowed astronomers to calculate the star's true brightness more accurately. A star's apparent brightness depends on both how much light it's actually producing and how far away it is. It's the difference between a candle next to your bed and a searchlight on a distant hill. Once you know the distance, you can work backward to figure out the star's actual luminosity. And luminosity, combined with temperature and chemical composition, is one of the key ingredients in the stellar aging recipe. By plotting Methuselah's precise position on the Hertzsprung-Russell diagram, that cosmic photo album of stellar evolution, astronomers could get a much better estimate of how long the star had been burning. But Hubble did more than just improve distance measurements. It also allowed for much more detailed analysis of the star's chemical composition. By spreading the star's light into a spectrum with extraordinary precision, astronomers could detect the faintest traces of different elements and isotopes. It's like having a cosmic forensics lab that can analyze evidence left over from the universe's earliest days. These improved measurements revealed subtle details that ground-based telescopes had missed. The exact ratios of different elements, the presence of trace isotopes, the precise temperature and surface gravity, all of these measurements contributed to a more complete picture of the star's history and age. The team also employed sophisticated computer models of stellar evolution, programs that simulate how stars burn their fuel and evolve over billions of years. These models are like cosmic time machines, allowing astronomers to watch the entire lifetime of a star play out in fast forward on a computer screen. By adjusting the initial conditions, the star's mass, composition, and formation environment, they could find the best match for Methuselah's observed properties. But perhaps most importantly, the new observations allowed astronomers to better understand the uncertainties in their measurements. Science isn't just about getting the right answer. It's about understanding how confident you can be in that answer. Every measurement comes with error bars, and understanding those uncertainties is crucial for interpreting results correctly. It's a bit like the difference between saying, "I'll be there at 3:0 and saying, "I'll be there at 3:0 plus or minus 15 minutes. Assuming traffic cooperates and I don't get distracted by interesting clouds. The second statement is more accurate, precisely because it acknowledges what we don't know for certain. As the new data came in, something interesting began to happen. The improved measurements didn't just give astronomers better numbers, they gave them better uncertainties. And those better uncertainties began to suggest that Methuselah's age, while still very old, might not be quite as impossibly ancient as originally calculated. The process was slow and methodical, involving multiple observing runs, careful calibration of instruments, and extensive cross-checking of results. It's the sort of work that rarely makes headlines, but forms the backbone of astronomical discovery, the patient accumulation of precise data that gradually brings distant objects into sharper focus. This wasn't just about one star anymore. The techniques being developed to study Methuselah could be applied to other ancient stars, helping to build a more complete picture of the early universe. Each measurement was like adding a piece to a vast cosmic jigsaw puzzle, slowly revealing the structure of space and time itself. And as the picture became clearer, so did the solution to the puzzle that had been troubling astronomers for years. The universe wasn't broken after all, their measurements were just getting good enough to see it clearly. Every star is a time capsule, carrying stories from the universe's earliest chapters. But some stars, like Methuselah, are particularly gifted storytellers, holding memories of a cosmos so young that it barely resembled the universe we know today. To understand what makes these ancient stars so special, we need to travel back to a time when the universe was simpler, stranger, and surprisingly empty. In the beginning, and by beginning, we mean about 400 years after the Big Bang, which in cosmic terms is practically the opening credits, the universe was a very different place. There were no stars yet, no galaxies, no planets, and certainly no astronomers to wonder about any of it. The cosmos was filled with a hot, dense soup of hydrogen and helium atoms with just a tiny sprinkle of lithium for variety. This was the cosmic equivalent of a pantry stocked with only flour, water, and a dash of salt. You could make bread, perhaps, but forget about chocolate cake or beef stew. The universe simply didn't have the ingredients for anything complex yet. All the heavier elements, the carbon in your pencil, the oxygen in your lungs, the iron in your blood, didn't exist. They hadn't been invented yet. The first stars that formed from this simple recipe are called population 3 stars, though no one has ever actually seen one. They were massive, brilliant, and short-lived, burning through their fuel in just a few million years before exploding in spectacular supernovas. These stellar pioneers were the universe's first element factories, forging carbon, oxygen, silicon, and iron in their nuclear cores, and then scattering these new ingredients across space when they died. Methuselah belongs to the next generation, the population 2 stars. These formed from gas clouds that had been lightly seasoned with the heavy elements produced by the first stellar generation. The recipe was still quite simple compared to modern stars like our Sun, but it was just complex enough to create stars that could burn for billions of years instead of millions. You can think of population 2 stars as the universe's teenagers, no longer the rambunctious children of the first generation, but not yet the mature, heavy element-rich adults like our Sun, which belongs to population 1. They formed when the universe was still young and wild, when galaxies were just beginning to organize themselves, and the cosmic web of dark matter was still weaving itself into the structure we see today. What makes these ancient stars so valuable to astronomers is precisely their chemical simplicity. Modern stars like our Sun are cosmic melting pots containing elements forged in dozens of previous stellar generations. Reading their composition is like trying to figure out a recipe after it's been modified by countless cooks over generations. But population 2 stars preserve the chemical signature of the early universe in their very atoms. Methuselah's spectrum tells a story of cosmic youth. Its atmosphere contains about 250 times less iron than our Sun and similarly reduced amounts of other heavy elements. This isn't because the star has somehow lost these elements, it's because they weren't available when the star formed. It's like finding an antique recipe that calls for ingredients that weren't available at the local market yet. This chemical archaeology allows astronomers to peer back in time and see what the universe was like when it was just a fraction of its current age. Every ancient star is a messenger from the cosmic past, carrying information about the conditions that existed billions of years ago. They tell us about the rate at which the first stellar generations enriched the cosmos with heavy elements, the structure of early galaxies, and the physics of star formation in the young universe. But these stellar time capsules also reveal something beautiful about the nature of cosmic recycling. The calcium in your bones, the iron in your blood, the oxygen in every breath you take, all of these elements were forged in the cores of stars that died long before our solar system was even a thought. Every atom in your body, except hydrogen, has been through multiple stellar lifetimes, cycling through the cosmos in an endless dance of creation and destruction. Methuselah represents an early chapter in this cosmic story. It formed when the universe had just begun the long process of chemical evolution that would eventually make planets and life possible. The star has been shining steadily for most of the universe's lifetime, watching galaxies grow and merge, seeing countless generations of younger stars born and die around it. In a sense, these ancient stars are cosmic librarians, preserving information about eras of the universe's history that we can study in no other way. We can't directly observe the early universe, but we can read its story in the light of its oldest stellar citizens. They are living relics, archives written in nuclear fire and preserved in starlight. This is why astronomers get so excited about stars like Methuselah and why they're willing to spend years making increasingly precise measurements to understand them better. These aren't just distant balls of gas. They're witnesses to cosmic history, repositories of information about the universe's youth that exists nowhere else. The fact that we can decode these stellar stories at all is rather remarkable. We're sitting on a small planet orbiting a middle-aged star in an unremarkable corner of the galaxy, using instruments no larger than a house to read the life stories of objects hundreds of times more massive than our Sun and hundreds of light years away. We can determine their ages, their compositions, their temperatures, and even their future fates, all from the faint light that reaches our telescopes. And sometimes, as in the case of Methuselah, these stellar stories surprise us. They challenge our understanding, force us to refine our measurements, and remind us that the universe still holds secrets waiting to be discovered. The star that seemed older than time itself became a teacher about the importance of precision, the nature of uncertainty, and the joy of solving cosmic puzzles one careful measurement at a time. In the end, these ancient stars remind us that we are all made of recycled starlight, participants in a cosmic story that began with the simplest elements and gradually grew complex enough to contemplate itself. Sometimes the most elegant solutions come from admitting our measurements weren't quite right. Not wrong, exactly, but not quite right enough to see the full picture clearly. In the case of HD 140,283, the resolution didn't require rewriting the laws of physics or discovering new types of time. It just required getting better at measuring very old things, which turns out to be harder than it sounds. The breakthrough came through a combination of improved observations and, perhaps more importantly, a better understanding of the uncertainties involved in stellar dating. Science has a funny relationship with uncertainty. The better you get at measuring things, the better you get at understanding what you can't measure precisely. It's like getting a clearer view of the edges of your knowledge. When astronomers took another careful look at Methuselah using Hubble's exquisite precision, they found that many of their original measurements were indeed accurate. The star's distance, its temperature, its chemical composition, these all held up under scrutiny. But when they fed these improved measurements into their stellar evolution models, along with more realistic estimates of uncertainty, something interesting happened. The star's calculated age began to come down. Not dramatically, we're talking about adjustments measured in hundreds of millions of years, which in stellar terms is like adjusting someone's age by a few months. But those few 100 million years made all the difference between impossible and merely ancient. The revised age calculation placed Methuselah at about 14 billion years old, plus or minus 0.8 billion years. That plus or minus part turned out to be crucial. Those error bars, representing the uncertainty in the measurement, meant that the star could potentially be as young as 13.2 billion years old, comfortably younger than the universe itself. It was a bit like discovering that your apparently 105-year-old neighbor might actually be anywhere from 97 to 105, which would make their birth during the supposedly impossible year of 1918 actually quite plausible. The neighbor hadn't gotten younger, you'd just gotten better at determining their actual age range. This resolution highlighted something important about how science works. The original measurements weren't wrong in any dramatic sense. They were based on the best available techniques and represented genuine attempts to understand a complex system, but they were precise enough to be confident while not being accurate enough to be completely correct. There's a difference between precision and accuracy that's worth understanding. Precision is about getting consistent results. If you measure something 10 times and get the same answer each time, that's precise. Accuracy is about getting the right answer. If your consistently measured answer matches reality, that's accurate. You can be very precise, but not accurate, like a clock that runs consistently slow, or accurate, but not precise, like a clock that's right twice a day, but otherwise random. In the case of HD 140,283, the original measurements were quite precise, but not quite accurate enough to account for all the subtle factors that influence stellar aging. The improved observations didn't just give better numbers, they gave better understanding of which numbers could be trusted and which carried larger uncertainties. Part of the improvement came from better stellar evolution models. Computers had gotten faster, allowing for more sophisticated simulations of how stars burn their fuel over billions of years. These models could account for subtle effects that earlier calculations had to approximate or ignore entirely. Things like the precise way convection carries heat through a star's interior, or how the star's composition changes as different nuclear reactions proceed at different rates. Another crucial factor was a better understanding of the star's exact chemical composition. Early measurements had focused on the major elements like hydrogen, helium, and iron. But the improved spectroscopic analysis revealed trace amounts of other elements that provided important clues about the star's formation, environment, and evolutionary history. It's a bit like the difference between knowing someone grew up somewhere in the Midwest versus knowing they grew up in a specific town at a specific time. The additional details don't just add information, they change how you interpret all the other information you already had. The resolution also demonstrated the importance of error analysis in scientific measurement. Every measurement comes with uncertainty, but understanding and properly accounting for that uncertainty is often more important than the measurement itself. The difference between 14.27 billion years old and 14 billion years old, plus or minus 0.8 billion years, isn't just about precision. It's about honest assessment of what we can and cannot know. Perhaps, most importantly, the resolution preserved both the integrity of our understanding of stellar evolution and our measurements of the universe's age. Neither had to be thrown out or dramatically revised. Instead, both were refined and improved through the careful application of better techniques and more honest accounting of uncertainties. This is often how science progresses, not through dramatic revolutions that overturn everything we thought we knew, but through gradual improvements in measurement and understanding that slowly bring reality into sharper focus. It's less like a sudden revelation and more like slowly adjusting the focus on a microscope until everything becomes clear. The case of Methuselah became a textbook example of how to handle apparent contradictions in astronomy. When observations don't match theory, the first step is to check both the observations and the theory more carefully. Often, the contradiction disappears not because either was fundamentally wrong, but because both needed to be understood more precisely. Methuselah earned a place in astronomical history, not as the star that broke the universe, but as the star that taught astronomers to be more careful about measuring very old things. It reminded the scientific community that precision without proper uncertainty analysis can be misleading, and that the most important scientific discoveries sometimes come from getting the details right rather than overturning fundamental principles. The star that once seemed older than time itself had become something even more valuable, a teacher about the nature of cosmic measurement, the importance of uncertainty, and the patience required to understand objects that have been burning since the universe was young. In trying to break the cosmic timeline, it had actually helped make that timeline more precise. Methuselah wasn't trying to break the universe, it was trying to show us how the universe really works. And once astronomers learned to listen properly, the star had quite a lot to say about cosmic history, stellar evolution, and the art of measuring things that are almost incomprehensibly old. The refined measurements of Methuselah didn't just solve one astronomical puzzle, they opened up new ways of understanding the early universe. By getting the star's age right, astronomers gained confidence in their ability to study other ancient objects. It's like learning to read a difficult handwriting. Once you figure out the technique, you can apply it to other letters from the same era. One of the most important lessons from Methuselah was about the early chemical evolution of the universe. The star's composition provides a snapshot of what the cosmos was like when it was about 800 million years old, still an infant by cosmic standards, but old enough to have witnessed the first few generations of stellar death and rebirth that began to seed space with heavy elements. The tiny amounts of carbon, oxygen, and iron in Methuselah's atmosphere tell a story of a universe that was just beginning to become chemically interesting. These trace elements represent the accumulated output of the first massive stars, the pioneering stellar generation that lived fast, died young, and left beautiful cosmic corpses in the form of scattered heavy elements. By studying stars like Methuselah, astronomers can trace how quickly the universe's chemical complexity grew. It's like having access to fossilized air from billions of years ago, allowing us to track how the cosmic atmosphere changed over time. Each ancient star preserves the chemical signature of its birth era, creating a timeline of cosmic enrichment that extends back to nearly the beginning of stellar history. But Methuselah taught astronomers about more than just chemistry. It also provided insights into the early structure of our galaxy. The star's orbit, that wide looping path that takes it far above and below the Milky Way's main disk, tells us about the chaotic conditions that existed when our galaxy was still assembling itself from smaller pieces. These halo stars are thought to be remnants of smaller galaxies that were absorbed by the Milky Way in its youth. They're like cosmic archaeology, preserving evidence of galactic mergers and the violent processes that built the large galaxies we see today. Each halo star is a survivor, a witness to the Milky Way's turbulent adolescence when it was still gobbling up its smaller neighbors. The study of Methuselah also helped refine our understanding of stellar evolution itself. The precise measurements needed to determine the star's age required astronomers to develop better models of how low-mass stars burn their fuel over billions of years. These improvements didn't just apply to one star. They made age determinations more reliable for entire populations of ancient stars. It's a bit like improving a recipe. Once you figure out the exact temperature and timing needed for one perfect cake, you can apply those techniques to bake better cakes in general. The lessons learned from Methuselah made astronomers better at reading the ages of other ancient stars, creating a more reliable cosmic timeline. The star also demonstrated the power of combining different astronomical techniques. The final age determination relied not just on stellar evolution models, but on precise distance measurements, detailed spectroscopic analysis, and sophisticated computer simulations. It was an interdisciplinary effort that showed how modern astronomy works best when different specialties collaborate. Perhaps more broadly, Methuselah became a case study in how science handles anomalous results. When observations don't match expectations, the scientific response isn't to ignore the problem or force the data to fit preconceived notions. Instead, scientists dig deeper, improve their measurements, and refine their understanding until the apparent contradiction resolves itself. This process of refinement has led to the discovery of other interesting ancient objects. Astronomers have found globular clusters that seem almost as old as the universe itself, white dwarf stars that serve as cosmic chronometers, and even more examples of extremely metal-poor stars that preserve chemical signatures from the cosmic dawn. Each of these discoveries builds on the techniques developed to study Methuselah. The star that once seemed impossible became a teacher, showing astronomers how to study the universe's earliest relics more effectively. It's like learning to read an ancient language. Once you crack the code for one text, you can begin to decipher entire libraries of previously unreadable documents. The broader impact extends beyond astronomy into our understanding of measurement and uncertainty in science. Methuselah reminded researchers across many fields about the importance of properly accounting for error bars and understanding the limits of precision. It became a textbook example of how apparent contradictions in science are often resolved not by dramatic revolutions, but by more careful analysis of existing data. The star also highlights the deep interconnectedness of cosmic processes. To understand Methuselah's age, astronomers had to understand stellar nucleosynthesis, galactic chemical evolution, stellar dynamics, and cosmology. The universe doesn't organize itself into convenient academic departments. Everything influences everything else in subtle but important ways. Today, Methuselah continues to be studied as new instruments and techniques become available. Each improvement in astronomical capability allows for more precise measurements, potentially revealing new details about the star's history and composition. It's like having an ancient manuscript that reveals new text every time you examine it with better equipment. The star has also inspired searches for even older objects. If Methuselah formed when the universe was about 800 million years old, might there be stars that formed even earlier? The search for these cosmic Methuselahs continues, each discovery potentially pushing our understanding of the early universe even further back in time. In the end, Methuselah exemplifies something beautiful about scientific discovery. A star that initially seemed to challenge our understanding of the universe ultimately deepened that understanding. It showed us that apparent impossibilities often hide opportunities for better measurement, more careful analysis, and deeper insight into how the cosmos works. The star that once threatened to be older than time itself became instead a guide to understanding time more precisely, a cosmic teacher disguised as a cosmic paradox. In the end, the star that seemed older than time itself became a teacher about the nature of time. Methuselah's journey from cosmic impossibility to refined measurement tells us something profound about how we understand the universe and our place within it. It's a story about precision, yes, but also about wonder, patience, and the beautiful complexity of measuring things that existed long before there was anyone around to measure them. Time, as Methuselah reminded us, is not as simple as we might think. We experience time as a steady flow, seconds ticking by at a reliable pace. But measuring cosmic time requires grappling with scales so vast they challenge human comprehension. A billion years is not just a very long time, it's a fundamentally different kind of time, one that spans the entire evolution of complex life on Earth, witnessed the birth and death of countless stellar generations, and saw galaxies dance their slow gravitational ballet across the cosmos. When we try to measure these cosmic timescales, we're essentially asking, how long has this star been converting hydrogen to helium in its core? It's a question that requires us to understand nuclear physics, stellar structure, galactic chemistry, and the expansion history of the universe itself. The fact that we can answer it at all, even approximately, is rather remarkable. The story of Methuselah also illustrates something important about scientific uncertainty. We often think of uncertainty as a limitation, a sign that science doesn't have the complete answer. But in reality, understanding and properly quantifying uncertainty is one of science's greatest strengths. The difference between saying this star is 14.27 billion years old and saying this star is 14 billion years old, plus or minus 0.8 billion years, isn't just about being more careful with numbers, it's about being honest about the limits of our knowledge. That honesty about uncertainty is what allowed the Methuselah paradox to be resolved. When astronomers included realistic error bars in their calculations, the apparent impossibility dissolved. The star wasn't actually older than the universe. Our initial measurements just weren't precise enough to account for all the factors that influence stellar aging. It's a reminder that confidence in science comes not from claiming absolute certainty, but from understanding and acknowledging what we don't know for sure. This has philosophical implications that extend beyond astronomy. In our daily lives, we're constantly making decisions based on incomplete information, estimating probabilities, and dealing with uncertainty. The scientific approach to uncertainty, measure carefully, understand your limitations, and be honest about error ranges, offers a model for thinking about many kinds of complex problems. The Methuselah story also demonstrates the cumulative nature of scientific progress. The resolution didn't come from a single brilliant insight or revolutionary discovery. It came from the patient accumulation of better measurements, improved techniques, and more sophisticated analysis. Each small improvement built on previous work, gradually bringing the star's true age into focus. This is how most scientific progress actually happens, not through dramatic eureka moments, but through countless small improvements in measurement and understanding. It's less like turning on a light switch and more like watching the sunrise, a gradual brightening that eventually illuminates the entire landscape. There's something deeply satisfying about this process. In a world where we're often told that science is constantly overturning itself, the Methuselah story shows science working as it's supposed to, identifying problems, developing better tools, and gradually converging on more accurate understanding. The fundamental principles of stellar evolution and cosmology didn't need to be discarded, they just needed to be applied more carefully. The star also reminds us of our connection to cosmic time. Methuselah has been shining for nearly the entire history of the universe, burning steadily while galaxies formed, while the first planets coalesced, while life emerged and evolved on countless worlds. It's a witness to deep time, a living link to the cosmic past that we can study and learn from. When you look up at the night sky, you're seeing light that left those stars years, decades, or centuries ago. But Methuselah's light carries something even more profound, a message from nearly the beginning of stellar time itself. The photons reaching our telescopes today began their journey when the universe was young and strange, when the first heavy elements were just beginning to seed space with the materials that would eventually make planets and life possible. This perspective can be both humbling and inspiring. We are brief creatures living on a small planet orbiting an ordinary star, but we're also part of a cosmic story that stretches back nearly to the beginning of time itself. The carbon in our bodies, the oxygen in our lungs, the iron in our blood, all of these elements were forged in stars like HD 140,283, scattered into space by stellar winds and supernova explosions, and eventually incorporated into new stars, planets, and living beings. We are literally made of ancient starlight, participants in a cosmic recycling program that has been operating for billions of years. Every breath we take connects us to the nuclear furnaces burning in stellar cores across the galaxy. Every heartbeat is powered by elements that were created when the universe was young and wild. The precision required to study objects like HD 140,283 also speaks to something remarkable about human capability. With instruments no larger than a house, we can determine the age, composition, and history of objects hundreds of times more massive than our Sun and located hundreds of light years away. We can measure stellar properties to a precision of a few percent across distances so vast that light takes years to cross them. This precision doesn't diminish the wonder of astronomy, it amplifies it. The more precisely we can measure the universe, the more clearly we can see its elegant complexity, its deep interconnections, and its remarkable consistency across vast scales of space and time. HD 140,283 taught us that the universe makes sense, even when our first attempts to understand it suggest otherwise. The star that once seemed to violate the cosmic timeline ultimately helped us understand that timeline more clearly. In doing so, it reminded us that the universe is both more mysterious and more knowable than we imagine, full of puzzles that challenge our understanding, but also full of clues that reward careful observation and patient analysis. And so we arrive at the end of our gentle journey through cosmic time, though really, time's story never truly ends. We've met a star that dared to seem older than everything, watched astronomers grapple with the impossible, and discovered how the universe sometimes teaches us its secrets by appearing to break its own rules. HD 140,283 still shines out there in the constellation Libra, no longer the troublemaker it once seemed, but instead a quiet teacher about precision, patience, and the beautiful uncertainty that drives all good science. It reminds us that the universe is both more mysterious and more knowable than we imagine, that our measurements can be wrong, but our methods for improving them are remarkably right. Tonight, as you let your thoughts drift towards sleep, perhaps you'll carry with you the image of that ancient star, still burning after nearly 14 billion years, still telling its story to anyone patient enough to listen. Time may be vast and sometimes confusing, but it's also wonderfully, persistently there, ticking along in stellar hearts and cosmic expanses, in your own gentle breathing and the quiet rhythm of rest. If you found any peace in this stellar mystery, if the wonders of deep time helped calm your thoughts, we'd be honored if you follow us for more quiet journeys through the cosmos. Thanks for joining us here at Sleep Science. Sleep well and dream of ancient starlight.